Okay, just a quick note. Still in the process of grading my part of the exam, so I should have everything done by this weekend for you and all the other assignments and so forth. We are in the middle of chapter 7. I hope to get it done today. But if I don't, I know there's a couple assignments, chapter 7 assignments due soon. I'll move those things around. Remember, I always will give you a day or two after we're done with the chapter to for the due date. But in the meantime, like I said, for the homework, at least there's two attempts. A lot of people go in there, do that first attempt, see how they do on their own, and then wait till we're done with the chapter and then complete the second attempt. So it's up to you, whichever works best for you. Okay. So any questions so far? We're getting close to chapter wise, we're getting close to half of our chapters, and we're already into the what do you call it? We call it the 45th day. At the 45th day, we need to check our students and see if who's dropped and so forth. So we're moving along pretty good. All right. Any questions? Yeah. Well, I'm going to continue with where we left off. Now, this particular chapter that we're dealing with is extremely important. Not to say that the other ones are not, but the concepts here are important because we need to grasp them. We need to grasp the fact that we can start drawing structures based on their valence electrons, and then we can actually, from the valence electrons, put a somewhat of a structure together, and then go to the shapes table, and with that information, actually give us a specific structure and name and a bond angle for all the compounds to be working with. We have talked before about electronegativity. We're going to talk more about it at this chapter because that electronegativity is extremely crucial with respect to the properties of these compounds that we make right now. Okay, and things like, for example, we did the HCN, and just by looking at it, I can tell you a couple of things. One, it's a linear molecule. Two, it's a polar molecule. Being a polar molecule, it's going to be more soluble in water. Okay, and if I look at carbon dioxide, I can tell you also tell you this information. One, it's also a linear molecule. Second, it has polar bonds, but it's nonpolar. So its solubility in water is very minimal, almost zero. Okay. And so that is all based on the structure we put together, it's based on the electronegativity of the bonds and so forth. Okay. And that's what I'm going to get you to when we're done with this chapter. So these are the structures we came up with. Okay. And the next slide basically just goes over the HCN kind of stepwise. So we identified what the center atom is. Okay. You'll be told, you'll be either written in bold or has an underscore, or be told in the sentence or so. Okay. So carbon is a central atom, and the nitrogen and hydrogen are bonded to the central atom. We add up the valence electrons from every atom. So we got one hydrogen, one carbon, one nitrogen. Remember way back in a couple of chapters ago, we were giving you structures, and we're asking you to count the number of atoms in that compound. This is what that part's all about, being able to identify how many of each atoms you have. This is pretty simple compound. So we got one hydrogen, one carbon, one nitrogen. Okay. Based on, and these are all always going to be the elements. So based on the group number, and that's why we went over the group number to tell us how many valence electrons they have, based on where they are on the group number tells you how many valence electrons. So hydrogen's in group 1A, hence 1 valence electron. Carbon's in group 4A, hence 4 valence electrons. And nitrogen is in group 5A. So for total, we have 10 valence electrons to work with. And like I stated, I like to divide it by 2 because that gives me pairs, because now I can just draw a line. A line represents a pair. Every bond is a line, and it represents 2 electrons or a pair. Okay, so this number is important because that is what you got to work with. You can't just magically add more electrons because you think that's where you need it, or if you have too many electrons at the end, take them out. You can't do that. You have 10 pair to work with, and you got to make those 10 pair work. A lot of times it's a real simple. We make the compound, everybody's bonded, and we're good to go. However, when we start checking the octet, we find that we don't have enough electrons on some atoms, but other atoms are happy with the octet. So we start creating double bonds and up to triple bonds. Okay. That's the limit. We don't have quadruple bonds. It's either a single, a double, or a triple. So there's no such thing as a quadruple bond. Okay. There will be 4 bonds on carbon, for example, but not a quadruple bond. All right. So then we add up the total valence electrons, and we can see just based on the formula that we have hydrogen and nitrogen bonded to the central atom. So I can very quickly bond them and create this hyphen, this line that represents through the pair. Okay, so those 2 pair that I utilize to actually create the first bond tells me now I got 3 pair to work with. Okay, and so the 3 pair that I got to work with, now I can place any I want on any atom that I want except hydrogen. Okay, except hydrogen. Why? Hold on, I got some people in here. Here we go. There we go. Because hydrogen has the duet rule. It does not have the octet rule. Hydrogen will only make 1 bond. Okay, so put that in long-term memory. Only 1 bond. So the hydrogen, I cannot add more hydrogens around hydrogen. So those 3 pair that I have, now I can put around carbon or nitrogen in any manner that I want. Okay, so here's the initial bond of the 2 elements, the hydrogen and the nitrogen. Okay, now I can add the other 3 pair around any element, and I chose here to put them around nitrogen, all 3 of them. Okay, you don't have to. You can put 2 of them on carbon and 1 on nitrogen, any combination thereof. You got 3, put them anywhere you want. I just like to pick the outside elements and work my way in. All right, so now double check to make sure that you have 5 pair. Remember, that is what we calculated, 5 pair. I go back to the structure I put together and I see I have 5 total pairs, so I'm good to go. I've not lost any, and this happens when you're drawing structures. In making the structures, you may lose a pair, or sometimes inadvertently you may add a pair. So double check and make sure you still have 5 pair. And here we do. Now to check the octet. Around hydrogen, remember it's a duet rule. Hydrogen's happy. Nitrogen has 8 electrons around it. Okay. 3 are lone pair. Remember the term lone pair. Those are not bonded. They're lone pair, all lone. Okay. And then 1 pair that is bonded pair. Okay. And it's shared with carbon. So it's happy. Carbon has 2 bonded pair, 1 shared with hydrogen and 1 shared with nitrogen. That's a total of 4. So it is not, the octet is not fulfilled there. So this is where you start borrowing, if you will, from Peter to give to Paul. Okay, when we start creating double bonds, you can see if I take, let me change this color a little bit. If I take that pair right there and I create a double bond, that's still going to put 6 carbons around, 6 electrons around carbon. So I can also take another pair and make a triple bond. Now everybody's happy. Okay, here it is. And so I come up with the structure. I go back as the last check your valence electrons, your pairs. Right now we have 5 pair. So I'm still consistent with what I had to begin with. Okay, I can't overemphasize this calculation right here, because this is where sometimes the majority, well, obviously the majority of times you'll see points taken off, is that the calculation was not based on the correct number of valence electrons. The other thing to check is you always will end up a number that is divisible by 2. Okay, I repeat, the number of valence electrons, you always have a number that is divisible by 2. And that, and never would you have an odd number. You always have a nice number divisible by 2. If you inadvertently said, all right, I got, instead of 10 electrons, you might check for yourself. Instead of 10, for some reason, you calculated 8, okay, or 4 pair. Well, when you start writing your structures, you can see that I don't have enough electrons, period, even to fulfill the octet. All right. And so that's another check. If I calculate 4 pair and then I come down to make my structure and I cannot make, no matter a double bond or triple bond, I'm maxed out, I can't make any more, then you can see there's a math problem. So go back and check the first step. Okay. The same is true if instead of 10 valence electrons, you calculated 12. So what happens now? You have an extra pair, right? And so you start making your formula and then you end up on an extra pair and you're like, well, I can't put it in the carbon because carbon's full. I can't put it in the nitrogen because nitrogen's full. And obviously I can't put it in hydrogen. So how did I get an extra pair? 12, okay? Or 6 pair, 12 valence electrons. So then again, that's a flag to tell you, check my math, check my valence, my math and my valence electrons. And so if you have less than the number you need, you're not going to have enough electrons to fulfill the octet. If you have more than it's what you're supposed to be having, then you're going to have too many electrons to put anywhere. Okay? So those are the 2 flags that tell you something's not right there. Okay. So now this takes us to what are called polyatomic ions. Now, what that means is this: you go to your shapes table or your periodic table, and if we look at down at the bottom left corner, we have what are called, it's labeled the most common polyatomic ions. Now, up to now, we've been talking about ions, positive and negative ions, cations and anions, as a single element. But there are ions out there that are polyatomic. They have more than one atom in them. They are a unit. They are not taken apart. That's important here, okay? They are a unit. For example, you have nitrogen. Let me highlight it. With 4 hydrogens bonded around it, and it has a positive charge. That polyatomic ion is a cation because it has a positive charge. You see the positive charge on the upper right, okay? That whole unit has a positive charge, and it has its own specific name. We don't change it. It's not, hydrogen, ammonia, nitrogen, anything like that. No, it has its name, which is the ammonium ion. Okay, the ammonium ion. Here's another one. Okay, it is a polyatomic ion where there is a hydrogen and an oxygen bonded together as a unit, and that unit has a, oh, bear with me for 1 second. I'm getting a quick phone call. I need to find out what's going on. It's important. 5 minutes. My apologies. I needed to take that phone call. Okay, so these are polyatomic ions, and again, as I stated, they are units that we utilize. You can attach these units with other cations to make compounds. So, all of the group 1 and group 2, all the metals that have a positive charge, okay, they're cations. I can mix them up with the anions here, so I can have things like sodium acetate, sodium hydroxide, potassium hydroxide, lithium hydroxide, so on and so forth. So you have now access to 5, 6, 7, 800 compounds that you can mix and match. Okay. And so what we're going to do is we're going to make the Lewis dot structure for these polyatomic ions. The process is the same. There's just two things that are a little bit different. One, we have to identify if it's an anion or a cation. Notice that the majority of them have a negative charge. Some have a -1 charge, some have a -3 charge. Okay, there are anions. There's only really one cation, the ammonium. Okay. All right, so we have to identify that one, the charge that they have, whether it's negative or positive, because that's going to determine whether we're going to add or subtract an electron from the valence count that we are going to do. Okay. And then the other aspect that we do is once we get that formula, and we do it the same way like we did with the ones that are the non-polyatomic ions, we find the general formula, we go to the shapes table, determine the structure, and then once we do that, we put a bracket around the polyatomic ion only, and then the charge on the upper right corner. Okay, so those are the two only different things that we do. One, add or subtract an electron depending on the charge of the polyatomic ion, and then finally draw the structure, put a bracket around the whole unit, and then put a charge in the upper right corner. Okay, so best thing to do is probably just to do an example. Okay. All right, so I'll do, excuse me, do all the same steps. Now, the next thing is, if it's a negative polyatomic ion, an anion, you need to add electrons. So if you have -1 charge, you add 1. If you have -3 charge, you add 3. Okay. If it's positive, we take away from the valence shell the number of its charge. If it's a +1 charge, take it away 1, +2, take away 2, etc. Okay. Then we can divide that number by 2 to give us the number of bond pairs, like we normally would if you wanted to do that. Then at the end, we draw the brackets around it, and we put the charge in the upper right-hand corner. Okay, so let's try the very first one. This was the ammonium ion. Notice that it has a positive charge. Okay, so being positive, we're going to subtract a 1 electron from the total valence electron count that we have. So we do the same thing like we've done before. 1 nitrogen brings in 5 valence electrons. 4 hydrogens, each one bring 1 electron. So we have a total of 9 electrons. Notice you have an odd number. So that tells you one or two things. The fact that you have a polyatomic ion, you're going to end up with a lot of times you're going to end up with a negative number. So that's a flag to tell you, oh, okay, I'm going to need to add or subtract. And this is where you got to remember, if you add or subtract, if it's a positive polyatomic ion, you subtract 1. So 9 minus 1 gives us 8 valence electrons, or 4 pair. The nitrogen is the central atom, okay? And you have the 4 hydrogens bonded around the central atom. So we can very quickly type the nitrogen and then the 4 bonded hydrogens around it. And guess what? That takes care of the 4 pair. Now you put a bracket. Notice it said bracket, not a parenthesis, a bracket around the whole molecule. and then the charge on the top right corner. Okay, this is right here, the charge in the top right corner. All right, and then the brackets right there. There's one there, and that signifies it to be a polyatomic ion. Okay, go back and check the valence electrons. We have 4 pairs, and sure enough, you got one there, that's 2, 3, and 4. Okay, so and there's 8 electrons around nitrogen and 2 around each hydrogen. Okay, so their form our structures is correct. Now, at this point in time, you can now do the general formula like you normally do. And so we have A, B, capital B, subscript 4. A is the nitrogen, and hydrogens, there's 4 of them around it. So the general formula is AB4. We go to the shapes table, and guess what we have? Here's AB4. So the ammonium ion has a geometry of tetrahedral, okay? And there's this 3-dimensional shape and a bond angle of 109.5. Okay, so we do the same thing as we would with the non-polyatomic ions. All right, well, let's do this. Let's do a few more examples. We have, all of them are anions. Notice we got a negative charge, okay? Now we have bromine here. This is bromine. Bromine is very special. It can't be, and when it's by itself, it's bromide. But here, bromine is a central atom, and there are oxygens bonded around it, okay? So this is not, has a special name. We'll get to that in a bit. So we got 1 bromine and 3 oxygens. Okay, so bromine brings in 7 valence electrons. There's 3 oxygens. Each one's in group 6, right? So that's 18. And so then it's a negative charge. So we're going to add a +1, okay, because of the charge. So that gives us a total of 26 valence electrons, or 13 pair. All right. So you can see here that, for example, we have, let me get the pen here. Let's see what I can do it here. And so we got bromine in the center, and we can very quickly put the oxygens on. Okay. So that takes care of 3 pair. So that leaves us 10. Okay. So here, like I said, I like to start around in the outside atoms and just work my way around. So I can, I'm going to change what's left over to a different color. All right. And so here I got 10 to work with. So I got 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, and then I got 9, so I need, where do I put the other one? Well, the only place left is in the center atom, right? Because the oxygens all have 8 electrons around it. Okay, bromine only had 6. So the only place I can put that last pair is in the central atom. Okay? That's why I like to go, I go on the outside, because I fill up the octet around the outside elements, and then what's left has to go in the center. And so we have put together the structure here. Let me clear all this. We end up with this. Okay. But the bracket, again, because it is an polyatomic ion and it has a -1 charge, and that's the formula, just exactly with what I just drew. The general formula is this, is AB3E. Right? A, B, because 3, because there's 3 oxygens, and E, because there is a lone pair on the central atom. That's AB3E for the general formula, which then we can go to, like we've done before, the shapes table and look for AB3E. And here we go. Okay, trigonal pyramid. You can see the lone pair sitting there in the central atom, and the 3, in this case, the 3 oxygens are on the bromine, and that bond angle is less than 109.5. Okay. All right, so that's that structure. The next one is the sulfate. Now you might say, oh, wait a minute, does that look reasonable? I mean, as far as the structure, sure. Why? Because if I go to the right there, oh, did I use this one? This one, yeah. Check it out right here, SO4 -2. We call that the sulfate. Okay, sulfate. So you get the sulfate ion, or in this case, anion, because it's a negative. More importantly, it's a -2 charge for that whole moiety, that whole group, SO4. If it were sulfur by itself with no oxygen, it would be called the sulfide. But here we got sulfur in the center and 4 oxygens bonded around it. Okay, with a full -2 charges, which is now it's a polyatomic ion called sulfate. All right, so let's continue with the valence electrons. We got 6 coming from sulfur. Okay, we have 4 oxygens in group 6, right? So 6 times 4 is 24. And now we have, it's a negative anion, so we're going to add 2 electrons because it has a -2 charge, okay? That means that we have 32 electrons or 16 pair. All right, so we do the same thing in drawing. So we start off with sulfur in the center, and then we can very quickly add 3 oxygens. Okay, so that took care of 4 pair. That means we got 12 to work with, right? So starting on the outside, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, go check all around there. Make sure you still have 12. Oh, there we go. Make it my marker out. 12, 13, 14, 15, 16. So we have a total of 16 pairs of valence electrons. So our structure is consistent with the number of valence electrons we have to work with. Okay. And so it is that structure right there with the bracket and the -2 on the upper right corner. Okay. We can also look at the general formula here. And that general formula is AB4, which if you look it up in the shapes table is simply tetrahedral. Okay. Tetrahedral. And then finally here, the SN negative. It's also a polyatomic ion. Going back to the table, you can see that it's called the cyanide ion, very poisonous ion. Okay. And same process as before. We got 4 valence electrons coming from carbon, 5 from nitrogen. it's a negative anion, so it's a -1, so we're going to add one electron, okay? Gives us a total of 10 valence electrons or 5 pair. There's only 2 atoms here, so there really isn't a central atom. It could be one or the other. Okay, if we have one more, like we did with HCN, we had to identify which one's the central atom. So it's a matter of just putting CN together. And I can do that here. I mean, I'm just going to basically just put C and N, okay? Right away, that's all it's bonded. That took care of 1 pair. And so you got 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5, 5 pair right there all together, which is consistent with the 5 pair we just calculated. Now we go check the octet. Nitrogen has 8 around it. Carbon does not. We're going to do the same thing that we did before. We're going to take a pair here and make double bond and actually go a triple bond. We're going to take 2 pair and make a triple bond between the 2. Okay, and that gives us that structure right there. So we count the valence electrons: 1, 2, 3, 4, 5 pair, which is consistent with what we created, what we calculated, I should say. So it's still 5 pair. We got the bracket and we got the negative charge in upper right corner. Don't forget the negative charge on them. Okay, and also it's a bracket, so it's not a parentheses. Okay, but by convention they use a bracket is utilized compared to a bracket. Let me try that again. A bracket is used instead of a parentheses. Okay. All right. So that's how we create the Lewis dot structure for polyatomic ions, which is the same procedure minus the adding or subtracting the electrons that we do for the neutral compounds, okay? Now, which brings us to this topic here, which is, we touched on it. I've been mentioning it to you that electrons, lone pair of electrons take up a lot more space and they have an effect on the bond angle of the rest of the molecule. And it's called here valence shell electron pair repulsion model, otherwise known as VSEPR. And it's all that wording just is exactly what I just told you. You got a pair of electrons, they're negative charge, they're going to repel each other. The fact that they repel each other has the effect on the bond angles of the rest of the molecule. Okay. All right. So I've already talked to you about this. You're familiar with the ABE general formula. A represents the central atom. B represents the atoms that are bonded to the central atom. And E represents the lone pairs that are on the central atom. I repeat, on the central atom. We don't care about the lone pairs on the other atoms, but only on the central atom. And you have a subscript for B and E, depending on how many atoms are bonded to the central atom and depending on how many lone pair are on the central atom, okay? Now, when you only have 2 atoms, it's pretty much straightforward. All the diatomics, that's Cn negative, the cyanide ion, there's only 2 atoms. It just stands to reason it is linear, okay, with respect to the shape. Now, we also have other compounds that are linear that have 3 atoms, but depending on how they're bonded, creates this linear geometry. Here, for example, carbon dioxide, because we're going to learn about this. Carbon dioxide is linear because of the double bond between the carbon and the oxygen. Okay, and that particular geometry, when we get to it, describes why carbon dioxide is a nonpolar molecule. Nonpolar molecule. Then we have another example of what we call trigonal planar. We have 3 moieties bonded to the central atom. A good example would be this species called This is the formula for formaldehyde, for example. Formaldehyde, you may have used it way back in high school days when you were maybe dissecting a pig or something. You had animals that were uh, kept in formaldehyde. I don't think they use it as much. It's been found that formaldehyde does cause cancer. But anyway, we have carbon in the central, double bonded to oxygen, and bonded to hydrogens on each side. And that bond angle all the way around is 120 degrees. Okay, that is called trigonal planar. Tetrahedral, which I mentioned, is probably the most common geometry with respect to the compounds, where you have a central atom and then bonded around it, you have four moieties. In this case, this is methane. This is the formula for methane. You got carbon and four hydrogens bonded around. Okay. Now the picture on the left is because we we draw in the two-dimensional world. The picture on the right is the three-dimensional model. So you can notice all the structures here on the far right. Those are the space fill model, the three-dimensional picture of these compounds. And so you can see how methane, you have, let me draw this. That bond right there, those four bonds, remember they carry electrons. And so they're going to repel with each other, not only with each other, but they're going to repel with the other bonds. And so they're going to put themselves in such a configuration to have maximum separation. And when that occurs, you end up with a tetrahedral configuration. They spread out as far away as they can from each other, and you end up with a bond angle of 109.5. Okay, another interesting one, and we would think SO2, because it's written like CO2, carbon dioxide, is sulfur dioxide. You would think that maybe carbon dioxide, sulfur dioxide would be similar to carbon dioxide being linear. Here's carbon dioxide, right? But don't forget, sulfur is in a different group. So it brings an extra pair of electrons. And the result is when we go to the structure, we end up putting a lone pair on the central atom. Okay, here's the lone pair right there. The result is that it spreads out. Those lone pair in the central atom causes that bond angle to crush in. Okay, we would expect it to be like the first example of formaldehyde we did earlier at 120 degrees, but because those lone pair in the central atom take up more space, they shrink that 120 degrees even more so. Okay, they shrink it to less than 120 degrees because of that lone pair. This structure is called bent, ABE. It's a general form AB2E, bent. And there again, we have the general formula, double bonded to one of the oxygens, single bonded to the other one. All right. Another one, this is the structure for ammonia. If you go through the valence electrons, you'll find there are all 8 pair of electrons that we work with. And you end up with the lone pair on the central atom. That in itself, again, like this guy here, you got a lone pair in the central atom, should keep in the back of your mind. That is a polar compound. The same is true here with the lone pair in the central atom. We have a polar compound. Hopefully it'll become clear here in a little bit when we start talking more about polarity. And then far right, you can see the blue represents a nitrogen, and that bond angle is split. That is less than, I shouldn't say split, it's less than 109.5. The tetrahedral, we would expect it, with 4 moieties around it, we would expect it to be 109.5. However, again, we have lone pair of electrons in a central atom taking up more space, causing the rest of the bonds to shrink in. And so that bond angle is much less. and then 109.5. Water, classic example here. Water has two lone pair. So that bond angle is even crushed in, bent in even more so. So it's really double less than 109.5 because of those four lone pair of electrons on the central atom, taking up quite a lot of space. Okay, resulting in water being extremely polar, very polar species. That water is the most polar solvent that we have, at least here on Earth. And excuse me. So to summarize this, you need to be able to review or be able to draw the Lewis dot structure of the atom, for example, and that's basically find the atom on the periodic table, find out how many valence electrons you have, and then put a dot. Okay. As far as structures are concerned, we add up the valence electrons. Okay. We tell you who the central atom is. We start putting bonds around the central atom, bonded to whatever elements we gave you, and then just fill in the rest with the valence electrons you come in until you get the octet has been fulfilled. If you don't have enough electrons and you have the correct number, okay, that you calculated, then start creating double bonds. And that doesn't work, create triple bonds. That's as far as you can go. If you still cannot fulfill the octet after doing all that, then go back and check your math. Maybe someplace somewhere you went, there's a problem in your calculation. All right. So practice on pH 3 in ozone. Ozone has it's 3 oxygen molecules. Here, just select one oxygen to be in the center. And let's see see if you can come up with that. And if you have questions about it, bring it to class. We can do it in class. Okay. I'm going to leave those to you. pH 3 and ozone. All right. Which brings us to bond polarity. And it's related to the structures. Okay. Very important. It's all hooked together. Okay, now we talked about covalent bonds where the electrons are shared, okay? When those electrons are equally shared, then we have what is called as a non-polar bond, okay? Because when they're not equally shared, what's happening is that on one side, there's more electron density than the other side, which results in a pole where one side has a higher negative charge and the other side has more of a positive nature to it, which results in a positive and a negative pole. Not a full charge like ionic compounds, okay? That's important, but a partial charge, okay? So if you think about this, all of the diatomic molecules have nonpolar bonds. Okay. When they are not shared equally, which is related to the electronegativity of the two atoms that are bonded, okay, we end up with a pole. Hence, we have a polar bond. Polar bond. All right, so we talked about electronegativity, just to rehash it. It's the ability of a bonded atom to attract the electrons in a bond toward itself. Fluorine, remember, was the most electronegative element, okay? And so we use fluorine as our benchmark to determine if we're comparing two other different atoms, and we use the distance they are from fluorine to determine which one has the higher electronegativity, okay? All right. We know that noble gases and our Chem 130 are not going to react. So nothing's going to happen since they got a zero electronegativity. And there's a general trend again that we talked about again before. In the top right corner would be fluorine. All right. Nonpolar bonds. All of the diatomic molecules are nonpolar. Why are they nonpolar? Because the elements are the same. Here's the problem. Here's a problem that I've seen in the past that people are not grasping. We have a diatomic element. We have two hydrogens bonded to each other. I had used the analogy of the tug of war, okay, where I had 200-pounder. Remember that? Well, those two 200-pounders are pulling on that rope equally. Okay, so here we have hydrogen, two hydrogens pull. The electronegativity is equal. Two oxygens, two nitrogens, two chlorines, two fluorines, etc., etc. The diatomics are equal, resulting in the nonpolar bond. I'm going to add one more example here, okay? And that is the carbon-hydrogen bond. Carbon-hydrogen bond is considered a nonpolar bond, okay? And the reason behind that is because the electronegativity, even though there's two different elements there, carbon and hydrogen, the electronegativity difference between the two is minimal, hence nonpolar. So when you look at the bond, if the two atoms are the same or they're carbon hydrogen, it's nonpolar. Okay, you don't have to go any further. That's it. It's a nonpolar bond. Okay? That means that if they're not the same, they're a polar bond. See what I'm saying? If the two elements are the same, it's a polar bond and includes a carbon hydrogen. It's a nonpolar bond, excuse me. If they're not the same, it's a polar bond. Okay. They're the same and carbon hydrogen, nonpolar. Not the same, polar bonds. You might think, why do I keep emphasizing that? Because this is a trouble child I've seen in the past as far as the concept of polarity, polar bonds, nonpolar bonds. And it's that straightforward. Don't make it more complicated. Okay. 200 pounds tug of war, same. I stick in a 400-pounder and a 200-pounder, that pulls different. Is the 200-pounder and the 400-pounder the same? No, they're not. They're two different weights. Okay. So we're going to have a polar bond there. All right. Enough of that. Let me move on. Carbon hydrogen, again, carbon hydrogen is considered a non-polar bond because the difference in their electronegativity is minimal. And essentially the same species. Okay, so in most covalent bonds between different nonmetals, one of the two atoms always will hold the atoms more tightly. Okay, because they have a higher negativity, resulting in a polar bond. That's what they're saying here. Okay, so if you have a bond, let's say between carbon and hydrogen, hydrogen and chlorine, or in this case chloride, sulfur and fluoride, silicon and nitrogen, guess what? Those are different atoms. Okay, so you don't have to analyze it for they're different atoms. Automatically, they're a polar bond. Okay, that's a polar bond between those two atoms, carbon and oxygen. All polar bonds. But what we're going to learn now, okay, well, who's pulling what? Okay, if it's a polar bond, then which atom is pulling the electrons? Well, this is where we get to the electronegativity. Okay, and what we do is we utilize an arrow with a positive charge at the end. And that arrow, the point of that arrow points at the atom that is most electronegative. And the positive side points at the atom that is the least electronegative. Now we also add another symbol, which is the lowercase delta. And this symbol right there, that means partial, okay? It is a partial, not a full-fledged charge like the ionic bonds. And the covalent bonds, there's a partial positive side and a partial negative. We have permanent, what are called permanent dipoles in this bond because of the nature of the beast. That is, the one atom is a lot more electronegative than the other, hence pulling the electrons tighter onto herself. We create, what is created is a dipole, a positive side and a negative side. More correctly, I should say a partial positive side and a partial negative side. I had used the example of the balloon in your hair, okay? We have created a partial negative side and a partial positive side. Taking that balloon, rub it on your head, okay? You transfer those electrons onto the balloon. You bring it to the surface of your chest. Those electrons are causing the electrons on your surface, because we get electrons all around us on the surface. It's causing the electrons on the surface of your chest and your shirt to go into your body, resulting in a more positive nature, if you will, on the surface of your shirt. So we got a more positive, partial positive area on your shirt. We got the net partial negative on the balloon. Guess what? They attach, and hence that balloon stays on your shirt for a short period of time. That's what's analogous to what's going on here. The difference is that in this case, it is a permanent dipole. What we do with the balloon is a temporary dipole. Okay, and it's permanent because of the nature of the bond and the two elements. Okay, so here we have fluoride, as we know, is the most electronegative element on the periodic table. So without even having to find out who's, find it, we know that. So if it's bonded to carbon, it's going to have a very strong partial negative charge on the fluoride, resulting kind of like the carbon being stripped of electrons, giving it more of a positive nature. Okay. And this is how we designate that with the polar arrow, with the point on the fluoride and the positive on the carbon. Now, if we go over to a bond that's between oxygen and hydrogen, okay, obviously fluorine's not involved here, but we look in the periodic table and determine who is more electronegative, oxygen or hydrogen. Well, you can see the hydrogen's in the far left. It's in group 1 of the periodic table, okay? And so oxygen's pretty close, right next to fluorine. So obviously oxygen is a lot more electronegative. Therefore, the arrow goes from hydrogen to oxygen with the partial negative on the oxygen. Okay. Another example of a polar bond. Now we compare phosphorus with chloride. Question is, who's more electronegative, the phosphorus or the chloride? Again, we use the periodic table. We see that chloride is right underneath fluoride, and phosphorus is in groups 5. It's further away, fluoride. So chloride here is a lot more electronegative. Hence, it tends to pull the electron density onto itself much more than the phosphorus, resulting in the arrow going from here, in this case, from left to right, with the partial negative on the chloride. Okay, so here are 3 examples of polar bonds. Notice in all 3 cases, there are 2 elements that are different. So automatically, I got a polar bond. The next step is determine which direction do I make the arrow go to. And that is determined by the polarity of the 2 atoms. That is determined by the electronegativity of the 2 elements and which one's more electronegative. And you determine that from its relative position on the periodic table. Now, there are tables out there you can look up the specific electronegativity, and you're welcome to do that, but it's not necessary because you just find this position relative to fluoride and you know which one's more electronegative. All right, so obviously noble gases, they're not going to bond, so we can there's no bonding going on with noble gases. Okay, the octet's full. Nothing's going to happen. They have zero electronegativity. And remember that fluorine or fluoride is the most electronegative element. Now, question here is add the delta notation and the polarity arrow. So the delta notation means we got a partial positive and a partial negative. Don't forget to add both. Okay. And then the arrow, the polarity arrow means that we got the point. The point is going to point toward the most electronegative element. So here we have a bond between carbon and oxygen. Find its position on the periodic table. Who's closer to fluoride? We see that oxygen is. And so we can draw the polarity arrow going from left to right, pointing toward the oxygen because it's a lot more electronegative than carbon is, and put the partial negative on the oxygen. Okay. Nitrogen and fluoride. No question here. You don't have to look up anything because fluoride is, hopefully you know by now, is the most electronegative element. And so automatically the arrow goes, in this case, from left to right with the partial negative on the fluoride. Now we got oxygen and hydrogen. We did this example earlier. Oxygen is a lot more electronegative. So in this case, the arrow can go from right to left. Now the arrow can go from right to left, left to right, depending on how you place the element. So it could have been written H-O. In that case, the arrow would have gone from left to right. Okay. And then we have chloride and carbon. Again, the chloride is a lot more electronegative. So in this case, the arrow goes from right to left with the partial negative on the chloride, partial positive on the carbon. Then we have carbon and hydrogen. None. Remember, carbon and hydrogen, their electronegativity is essentially the same. So we treat it as a diatomic. Okay. Therefore, it's nonpolar. There's no arrow to place here. All right. Question here says, which bonds are ionic, which are polar covalent, and which are non-polar covalent? And these typical questions here. All right. So the first question is asked is, which bonds are ionic? Okay. Well, ionic, if you recall, an ionic bond requires a combination of a metal and a non-metal. Okay. So if we look through these choices here, there's only one metal and non-metal choice, and that's a sodium chloride. Bromine and bromine are non-metals, phosphorus and fluoride non-metals, fluoride and bromide non-metals. Okay. But sodium and chloride is a metal non-metal combination, therefore it is an ionic bond. So the rest of them are covalent bonds. Now the question is, which of the covalent bonds, which ones are polar and which ones are non-polar? All right. If they are non-polar covalent bonds, they're going to be one or two things, a diatomic or a carbon hydrogen. Okay. Well, we got no carbon hydrogen here, but we do have a diatomic. That's bromine. That means the rest of them are polar covalent. Okay. See how we went through that? First one was ionic bonds. We know sodium chloride is ionic. That means the other three choices are covalent to determine which is polar, which is nonpolar. If it's nonpolar, that means that the two atoms have to be the same or the carbon hydrogen. And we only have one example of the two atom elements have being the same, and that's bromine. So bromine's nonpolar. Okay. That implies that the rest of them are polar. Okay, so polarity, very important. Okay, we'll be using it over and over again quite a bit. So, and like I said, when it talks about the polarity, is basically a tug of war of these bonded electrons. One of them is going to be pulled toward the other due to the electronegativity of the other atom. So one atom is always going to win the tug of war. when they are different atoms. The only exception is carbon and hydrogen. Nobody wins the pull there. They're both the same, okay? It's a tie, if you will. Here we're going through some more examples. You want to know ionic, polar, nonpolar? Okay, so the first one, sodium chloride. Automatically, I got sodium right up front. That is an ionic compound, okay? No question asked. Hydrogen and chloride. Well, it's not ionic because there's no metals there. Two nonmetals, hydrogen and chloride. They're not the same, therefore it is nonpolar. It wouldn't be nonpolar, so it's got to be polar, right? Polar covalent, because the two atoms are different. Next example, hydrogen, hydrogen. The atoms are the same, covalent bond. Being the same means it is nonpolar, okay? Chloride and carbon, again, covalent bond. The two atoms are different. It's a polar. Carbon and hydrogen. It's a covalent bond, but we treat carbon and hydrogen as far as electronegativity the same. Therefore, it's a nonpolar covalent bond. Oxygen and oxygen, covalent bond. They're both the same. It is nonpolar. Potassium and oxygen. We got a potassium, which is a metal, and oxygen, which is a nonmetal. Ionic compound, you don't have to go any further, okay? And phosphorus and fluoride, both nonmetals, both different nonmetals, polar covalent, okay? All right. Now, of these here, the ones that are the ionic, let me change the color. The sodium chloride, and which is ionic bond, and the potassium oxygen, which is also an ionic bond. Those guys, those chemicals, when they're put in water, again, they dissociate completely to a full negative charge and a full positive charge. They form the ions. They form the electrolytes. You're familiar with the term electrolytes because you got electrolyte products that are out there that they want you to drink. Okay, they're ions. Okay, now the other ones don't do that. When you put those guys in water, they do not dissociate completely in water. They will stay intact, but they will show solubility in water because of their polar character. And so those other covalent, all the polar covalent compounds will show more solubility in water than the nonpolar covalent. The nonpolar covalent will show more solubility in oil, if you will, into nonpolar solvents. Okay. All right. Now, the other aspect too is drawing the arrow. If I need to draw the arrow here, it's going to go from hydrogen to chloride. Nothing for hydrogen. It's going to go from carbon to chloride. Right to left for the other polar solvent. Nothing for the nonpolar. Nothing for oxygen. And then from the phosphorus and sulfur, it will go from left to right. Okay. With the partial positive on the fluoride. All right, so let's clear this up a little bit. Now, when a molecule has all nonpolar bonds, repeat, when a molecule has all nonpolar bonds, that means that the molecule itself would be nonpolar, okay? So if a molecule has all nonpolar bonds, let's say all carbon and hydrogen bonds, you have a nonpolar molecule. If the polar bonds do not cancel out, if you have polar bonds that do not cancel out, you have a polar molecule. Let me explain this. This is a little bit of a challenge sometimes. Remember the arrow that we were drawing. Okay, well, there's a name for that type of an arrow. It's called the vector. Okay, now we're not going to get into the details of that, but basically a vector is this. A vector is something that has magnitude. Let's say if I say to you 20 miles, well, 20 miles doesn't mean much. It's just 20 miles. But if I say to you 20 miles north, now you got direction. And so a vector has direction and magnitude, okay? Meaning that these arrows can be, just by looking at the arrows, I can add them together. If they're going the same direction and they're the same length, then I can add those two arrows together. So I got two arrows. If they go in opposite direction, they can cancel each other out, okay? So if I have, for example, let me draw two arrows. If I have this arrow going to the right and this arrow going to the right, the force, the actual magnitude, I can double. They double up, whatever the value is. There's a value between it in that arrow on the left and value on the arrow on the right. So it's cumulative, okay? Because they're going both in the same direction. Now, if I got one going to the right, but the other one's going from in the same direction, but in the opposite direction, okay, guess what? They cancel each other out. So the arrow on the left, the one I just wrote, change the color, change a little bit. And so the arrow going on the left, the red one, and the yellow one going toward it in the same direction, they cancel out. So I end up with a net zero here if they had the length of the arrow is the same magnitude. Let's assume it is. Now, whether I have it going like this or like this, that also cancels out, okay? So you can see the arrows up here in the sulfur dioxide. One arrow is going this direction and the other arrow is going in this direction, so they do not cancel out. That arrow represents the polarity of that bond. And these two arrows do not cancel out. The result is that you end up with a polar molecule because the polarity of the bonds do not cancel out, okay? Compared to, let me clear this up a little bit. All right, so if they cancel each other out, we end up with a nonpolar bond. For example, carbon dioxide. If we go through the Lewis dot structure, we end up with a structure that looks as linear structure right here, which is AB2, carbon dioxide. For sulfur dioxide, remember that will be AB2E, okay? It's totally different. And because those lone pair are sitting on the central atom right there, that causes that bond angle to be less, okay? And there's no canceling out that bond. If those bond angles were equal, they'd be all canceled out. They're not, okay? Over here, we have a polar bond. The bond between the carbon and the oxygen on the right-hand side is polar. The carbon in that bond between the carbon and oxygen on the left-hand side is polar. Carbon dioxide has two polar bonds, but because of the structure of the molecule, because the arrows go in opposite directions from each other, guess what? The polarity cancels out. And with the polarity canceling out, we end up with a non-polar molecule, right? And so when polar bonds do not cancel out, we have a polar bond. And there's another example where bonds cancel out, and that's in the tetrahedral configuration. Right here. If we have polar bonds, if we have four polar bonds, on the tetrahedral, and let's say it was carbon with 4 chlorides, carbon tetrachloride. Carbon and chloride. Yeah, let's assume that the bonds on the outside, they have 4 chlorides, carbon tetrachloride, 4 chlorides. The bond between each carbon and each chloride is a polar bond. Okay. But in this configuration with tetrahedral, those 4 polar bonds cancel out, resulting in having a nonpolar species. Okay. And so there's another example of the bonds canceling out. All right, what we got here? Oh, somebody's upset here. Anyway, I'm getting close to the time here. Why don't we stop it here? Let's see. Actually, let's do this one here. We're going to be done with this chapter. I got 2 slides. So bear with me, and we'll knock it out real quick. It's very short. All right, carbon, methane, carbon and 4 hydrogen bonds. Carbon, hydrogen, there's 4 bonds around the carbon. Each one is nonpolar. So the molecule is nonpolar. Okay. Now, the phosphorus trichloride. This example is the, let me see if I can draw it. We have, if we go through the Lewis dot structures, and this is where that comes into play, we end up with, bear with me. We end up with phosphorus, chloride. This is chloride there. Sorry, my little pen's not doing so good. Okay. And you end up with a lone pair on the phosphorus. Now, you would think this would be tetrahedral, but it's not because of the lone pair. Okay, this general formula would be AB3E. Okay, it's got a lone pair in there. That means that these bond angles is much less than 109.5, which means that the bonds do not cancel out, thinking that they will be tetrahedral. But because of the lone pair there, these bonds, let me change the color. The dipole in each bond goes from the phosphorus to the chloride, phosphorus to chloride, that direction, and they don't cancel out, and you end up with a polar bond. Okay. And then carbon dioxide, we just talked about it. When you go through the Lewis dot structure, you end up with carbon double bonded to oxygen. Oh, that's a double bond. Each carbon oxygen is polar, but they cancel each other out. So we result in a nonpolar molecule. Okay. And so the CH4, all nonpolar bonds, automatically polar molecule. The PCl3, if you go through the Lewis dot structure, you end up with a lone pair on the phosphorus, automatically polar molecule. Carbon dioxide, when you go through Lewis dot structure, becomes linear. We can see that the polar bonds of the carbon and oxygen cancel each other out. Therefore, we end up with a nonpolar species, okay? Which then affects the properties down the road that we're going to be talking about. All right, so you might want to practice this. We've done water and we've done ammonia, but you might want to go back and determine whether, for yourself that it is a polar molecule, determine the bonds, are they polar bonds, okay, to help you out, and go through the whole thing, the shape, draw the Lewis dot structure, determine the shape, and the bond angles. Determine the bonds are polar and if the molecule is polar. Okay, run through that scenario. If you have a challenge with it, bring it back to class and we will talk about it. Okay, guess what, folks? Congratulations. Chapter 7 is complete. All right, so